Okay, so welcome back to this video in which we are trying to prove that if we have a set of Cauchy, if we have a sequence of Cauchy, if we have a Cauchy sequence of sequences which are within the subset C of L infinity, then what we are assured is that that is a Cauchy sequence firstly in the larger set L infinity, in the larger metric space L infinity, and that therefore it does converge to some other sequence L, which is within that larger metric space L infinity. But now what we want to show is that if all of these sequences are convergent themselves, and this sequence of sequences converges to L in the D infinity metric, then it implies that this sequence which they are converging to is going to itself be a convergent sequence, and which implies that this sequence which they're converging to is also an element of the set C, which is this set of all convergent sequences, which implies that any Cauchy sequence of sequences that are in the convergent in the set of convergent sequences is going to converge to another element of the set of convergent sequences. Sorry, the subset of convergent sequences, and therefore that set with that D infinity metric forms a complete metric space. Okay, so what we need to do to show that is show that this sequence here is a Cauchy sequence, i.e. that if there exists some big N such that if I take any little n and any little m that are greater than or equal to big N, then the distance, the modulus of Ln minus Lm, is going to be less than epsilon. So we said let epsilon be some arbitrary number greater than 0. So let epsilon be greater than 0. I need to show there exists a big N, which is an element of the natural numbers, such that if little n and little m are greater than or equal to big N, it implies that that is true. Okay, so the way we're going to do this is we're going to use the fact that this sequence of sequences converges to L in the D infinity metric. So the convergence of this sequence, so this sequence S, which is the sequence S1, S2, S3, etc., it is converging to L, and in the metric D infinity. So I might put, sometimes you'll see people put the metric we're using there, D infinity. That means that for all, let's say we won't use epsilon, we'll use, or for all delta greater than 0, there exists, we'll use H, capital H, which is an element of the natural numbers, such that if little h is greater than or equal to big H, it implies that the distance, the D infinity distance of the sequence S little h and this sequence L is going to be less than epsilon. So that's just the definition of convergence. It's just saying, okay, you give me whatever little number you like, I can find you, so, oh sorry, don't do that. You give me any little number you like, I can find your point in this sequence, such that if you take any term beyond there, that the distance between them is going to be, the distance between that term and the limit of the sequence is going to be less than epsilon. Okay, so now we just apply the definition of this distance, this D infinity. Well, S little h, so S little h, I'll draw it up here. S big H is some sequence up here, so we'll have X big H1, X big H2, X big H3, etc., and X little h, which will converge to some D big H, and we've got some S little h here, which is X little H1, X little H2, X little H3, etc., and that will converge to D little h. And whatever sequence you pick that is greater than or equal to big H, I can assure, the distance between that sequence and L is going to be less than infinity, delta, basically. And if we just fill now in what this distance is, it was defined, remember, to be the supremum over I as an element of the natural numbers of the modulus of the term, of the modulus of the difference between corresponding terms, basically. So you take the first term here, you subtract off the first term of this sequence, and you take its modulus. You then do the same for the second terms, the third terms, the fourth terms, and you take the supremum over all I as an element of the natural numbers. So the supremum of the difference in the terms of this and the terms of this over all terms. So the ith term of the H sequence is xhi, and the ith term of this limiting sequence L is li. So it's the supremum over all I is an element of the natural numbers of these modulus of xhi minus li, basically. Okay, so basically what this is saying is that if you take any sequence s little h which is beyond s big H, then if you take the term xhi, the ith term, and you compare it with the ith term of this limit, then that has to be less than epsilon, because if the supremum over all I is an element of the natural numbers is less than epsilon, then that implies that this, remember this is a supremum of a set, so this is the supremum of the set containing the modulus of xhi minus li for all I is an element of the natural numbers. So if this is less than epsilon, then it implies that all the elements of this set are strictly less than epsilon as well, which implies that xhi minus li, the modulus of that, is less than epsilon for all I is an element of the natural numbers, because it's for all elements of this set, and this set has elements ranging over all I is an element of the natural numbers. Okay, so what that implies is that if you take the ith term of this H sequence here, and you subtract off the ith term of this limiting sequence here, then the difference between them is going to be strictly less than epsilon, and that works not only for all terms, so whatever term you take of this H sequence, but H, remember, was arbitrary. I can pick H to be any number that is greater than or equal to big H. Okay, right, so I'm now going to say let delta equal epsilon over 3, basically. Let delta equal epsilon over 3, and then make this big H so that all of this is true for delta is equal to epsilon over 3. And I do apologise. Here, when I put that should have been delta. This should have also been delta, this should have been delta, and this should have been delta here. I was using epsilon just because that's what I'm used to using, but we didn't want to use epsilon because we've already used epsilon up here. So I'm now letting this delta equal epsilon over 3, and I'm saying I can find you a point, a big H, which is an element of the natural numbers, such that if you take any sequence s little h, which is beyond this sequence s big H, then the distance between them is going to be less than epsilon over 3, and that implies that whatever term you pick of those sequences, then the distance between that term and its corresponding term in this limiting sequence is going to be less than epsilon over 3. Okay, right, so just pick one. Pick any sequence, basically, that satisfies this property. So I'm going to pick the sequence big H, the sequence S. Pick S big H. So we're going to use this sequence big H. And remember, what we've now seen is that I've chosen big H deliberately so that this is going to be true, i.e. that the modulus of x big H I minus Li is going to be less than epsilon over 3. So if I draw out the sequence S big H, it's going to be equal to x big H1, the first term of the sequence, x big H2, the second term, x big H3, etc., all the way on, and you'll have an arbitrary term, x big Hi, and then you've got this sequence L, basically, and this is L1, L2, L3, etc., all the way up to Li and onwards, so we'll put that ... Okay, but this is basically just a special case of here, because I've chosen big H so that you can do that, so that this is going to be true. Because I've chosen big H, because this sequence of sequences converges to L, it's always possible to pick a big H such that this is true for all I. i.e., if you take this term and subtract this term, take the modulus, it's going to be less than epsilon over 3. Do that for whichever term you like, it's always going to be true. So the distance between all of these terms here is going to be less than epsilon over 3. So that's why I've just chosen this sequence arbitrarily. You could have chosen any of the sequences beyond S big H. So you could have chosen any little h which was beyond big H. I've just said, okay, we'll use big H. Big H will do, basically. Okay, right, so, now another piece of paper. Right, so, what we now want to do is, we want to, this sequence, S big H, is convergent, because all of the sequences S in the sequence that was converging to L were convergent. We started off by saying we've got a sequence of convergent sequences. So this is a single term of that sequence, so it converges to some D big H, basically. Okay, now the fact that it is convergent, it's a convergent sequence of either real or complex numbers, that implies that it is a Cauchy sequence. So it being Cauchy, so S big H is a Cauchy sequence. And what does that mean? That means that for all, and I need another letter now, for all eta greater than 0, there exists a point, we'll say, what should we call it this time? We'll say there exists a big Q, which is an element of the natural numbers, such that if little p and little q are greater than or equal to big Q, it implies that the distance between the pth term, so let's say x big HP minus x big HQ, the qth term, is less than eta. So basically, if I look at this sequence here, which is this sequence S big H, I can find you some point, let's say x big H big Q, such that whatever eta you give me, I can find you a big H such that if I take any big Q, such that if I take any two terms beyond that term in the sequence, or equal to that term, you could pick that term itself, but any two terms in this tail of the sequence, and you ask how far away are they in the metric space of the real or complex numbers, then that's going to be less than eta, strictly less than eta. Okay, now we're done, I claim, because what we were trying to do, remember, was we were trying to prove that this sequence L was convergent, i.e. we were trying to find some L big N such that for that tail end of the sequence of L, if you picked any 2 points, L little n and L little m, then their distance, the modulus of L little n minus L little m, was going to be less than epsilon. Okay, so I'm going to set eta, let eta equal epsilon over 3 again. I can find you a big Q, so set big Q such that eta is equal to epsilon over 3. So find a big Q such that if you pick any two terms that are within this tail end of the sequence, then the distance between them is less than epsilon over 3. So you can do that. Okay, right, and now we're done, because I'm gonna say, let this big N, we're trying to find this big N, I'm saying let this big N equal Q, let big N equal Q. And I claim that if I take any little n and little m, which are greater than or equal to this big N, which is equal now to Q, then what I need to show you is that the distance between those two, so the distance between L little n and L little n, is going to be less than epsilon. And the way I'm going to do that is I'm going to say, okay, the distance between Ln and Lm is less than the distance from Ln to its corresponding term in this sequence up here. So xh big N, and don't worry, I will draw a picture to show you exactly what's happening, plus the distance between x big H little n to x big H little m, plus the distance of x big H little m to Lm, basically. Okay, and I've set this up so that all those distances are going to be less than epsilon over 3. So intuitively, this is what we're doing. We have this sequence S big H, okay, which is this sequence here, x big H1, x big H2, x big H3, and then we went up all the way to x big H big Q, which was this special number such that if you took any two numbers beyond there, if you took any two elements in that tail of the sequence, then the distance between them was going to be less than epsilon, basically. Epsilon over 3, sorry. So x big H little p minus x big H little q was going to be less than epsilon over 3 if p and q were greater than or equal to big Q. Okay, now we've got this sequence down here, which is L, which is the sequence L1, L2, L3, and then we go up to L big Q, and I've set this big N equal to Q. So what I claim is if I take any 2 points in this tail end of the sequence, L little n and L little m, then their distance is going to be less than epsilon away from each other. I want to show that the modulus of ln minus lm is less than epsilon. Okay, so what I've said is go back to this sequence and find its corresponding term. Find the nth term of this sequence, x big H n, and find the corresponding term for this one, x big H m, which will be in the tail end of this sequence because little n and little m were assumed to be greater than or equal to q. So their corresponding terms in this sequence s big H are also going to be within that tail end back there, basically. Okay, and now what I've said is that the distance between these two terms, which is this pink thing here, so I'll highlight it, pink here, okay, is going to be less than or equal to the distance from ln to this corresponding term here, which is that distance there, plus the distance from that term here to this term here, plus the distance from that term here to this term here. So that's overall what we've done, and I've used the same pink twice, which is annoying. Let me get the blue to, so this one is blue now, so this is blue there, okay? Right, that's messed it up, never mind. Okay, so that's just the triangle inequality in the real or complex numbers, basically. But I assured you that if you picked P and Q that were greater than or equal to big Q, that the distance apart of those two terms, if I picked two terms in this tail end, their distance apart was epsilon over 3. That's how I found big Q. So this distance here is less than epsilon over 3. Okay? But how did I pick big H? Big H was the point in the sequence of sequences where after that point the distance between SH and L was less than epsilon over 3, remember? So I picked SH, remember, such that the d infinity of S big H to L was less than epsilon over 3. And that implied, by the definition of d infinity, remember the definition of the d infinity is the supremum over I as an element of the natural numbers of the modulus of x big H I minus Li, i.e. take a term in here, take its corresponding term in here, and that distance, take the distance between them and take the supremum, that was going to be less than epsilon over 3. So that implies that for all I as an element of the natural numbers, x big H I minus Li was going to be less than epsilon over 3. So in particular, these distances here, the distance between these two corresponding terms, the nth term, so just let I equal little n, and its corresponding term L little n in this this limit here, this sequence which is the limit of this sequence of sequences, is going to be less than epsilon over 3. So again, I can make that less than epsilon over 3, and for the exact same reason, just let I equal little m, I can make this distance here, this distance between the nth term of this sequence SH and the nth term of the sequence L, I can make this less than epsilon over 3. So, when I add them all together then, when I add up the distance from ln to xh little n, plus the distance from h little n to xh little m, the nth term of the h sequence, plus the distance of the nth term of the h sequence to the nth term of the L sequence, that is overall going to be less than epsilon. But this thing is strictly greater than or equal to. I should have put greater than or equal to, sorry. That should have been greater than or equal to. It was the triangle inequality. I apologise for that. That's going to be greater than or equal to ln minus ln. So again, what I've done basically is I've found you I've shown basically that if you take any 2 points in here, then the distance between them is going to be less than epsilon by the transitive property. If this is less than or equal to this, and this is strictly less than epsilon, then this is going to be strictly less than epsilon as well. So, what I've shown is that if we use big Q as our big N, then if you take any 2 points, L little n and L little m, that are beyond that point in this sequence, which is a limit, the limit of this sequence of sequences, then they are going to be within epsilon of one another. So this sequence, this L sequence, which is the limit of the sequence S1, S2, S3, etc., it converges, remember, on L. L is now going to be, if all of these sequences here are convergent sequences, which, i.e. the elements of C, then it implies that L is also a Cauchy sequence, and of course we know that because the real line and the complex numbers are complete, any Cauchy sequence of real numbers or complex numbers is going to be convergent, so this implies it's convergent. So it implies that L is an element of C, which implies that if you take any Cauchy sequence of convergent sequences, so any Cauchy sequence of sequences in this metric space C with the d infinity metric, then it will converge in L infinity, and in fact the thing it converges to will actually be a convergent sequence itself. So in fact it will converge to something in C itself. So what we've proven is that any Cauchy sequence in this metric space C with the metric d infinity on it will converge to an element in that metric space, and therefore that metric space is a complete metric space. Thank you very much.